Hi! In this video, you will learn about the independence of random variables, which will turn out to be a really important property. Independence probably sounds familiar to you. Indeed, you already know about independence of events. We say that two events are independent if the probability that they occur both is equal to the product of the probabilities that they occur separately. We could also express this using conditional probabilities. Either all three of these properties hold and then the two events A and B are independent, or none of them hold and then A and B are dependent. In this video, I want to talk about independence of random variables instead of events. Well, let's start with an example. Suppose you throw two dice, and the random variable S is the sum of the two dice, and M equals the maximum numbers of spots per dice. In this example, S equals 7, while M equals 4. Intuitively, do you think these two random variables are independent? Well, probably not, because if you know that the maximum equals 3, for instance, the probability that the sum equals 12 is just 0. Since if the maximum is 3, the two dice can both be at most 3, and the sum then obviously cannot be 12, right? And this 0 is clearly not equal to the product of the two probabilities, which are both non-zero. So the event maximum is 3 and sum is 12 are dependent. Therefore, it seems reasonable to say that the random variables sum and maximum of the two dice are also dependent. Indeed, we will say that two random variables, x and y, are independent if all events involving x are independent of all events involving y. For discrete random variables, we may therefore require that this condition holds for all values a and b. If this condition does not hold for some a and b, as was the case in our sum and maximum example, then the two variables are dependent. Unfortunately, for continuous random variables, all these probabilities are 0. So the equation would always hold, and then this would be a useless definition. However, inspired by the distribution function, maybe we can still use RID, but now with inequalities rather than equalities. Notice the small change in our definition. This will allow us to cover both the discrete and the continuous setting with this single definition. Of course, if we define independence in two different ways, as we just did for the discrete case, we should check whether these two conditions are equivalent. Well, let's start with the following discrete example. I have here one Dutch coin and one French coin. I toss the Dutch coin 3 times. I call x the number of tails I get. And I toss the French one 4 times. I call y the number of tails I get for the French one. Suppose both are fair coins. At every toss, there is a probability 1/2 to get tails. This leads to the following probability table. Feel free to take some time to check this. By our first definition, it is clear that x and y are independent. Indeed, the probability that x is a and y is b is equal to the probability that x is a times the probability that y is b. In other words, each cell value is the product of the row sum and the column sum. Here you see that that is true for x is 1 and y is 3. To see that this probability also factorizes when we talk about inequalities, let's take a look at the probability that x is less than or equal to 2 and y is less than or equal to 1. That corresponds to the highlighted region in our table. The probability for this to happen can be calculated by taking the sum of all probabilities in this region. So the probability is the sum of these 6 probabilities. However, by the independence we already established, we can factor all these probabilities. Rearranging we get that indeed this probability is equal to the probability that x is less than or equal to 2 times the probability that y is less than or equal to 1. This was of course just an example, but this approach always works. Now let's shift our focus to continuous random variables. Consider 2 light bulbs, one in my kitchen and one in my living room. Let's call x and y the lifetimes of these light bulbs. We can model them by an exponential distribution, which is often a good choice for lifetimes. For instance, x has an exponential distribution with parameter 0.25, which means that its expected lifetime is 4 years. And y has an exponential distribution with parameter 0.2, which means that its expected lifetime is 5 years. Now, what is the probability that I need to replace at least one of them in the upcoming 3 years? Well, that is the probability that x or y is less than 3, or they both are. It is easier actually to look at the complement. X and y are both at least 3. Meaning that I do not have to replace any light bulbs in the next 3 years. These light bulbs are physically independent of each other. They are in different rooms. As a result, these random variables are also independent. This independence mirrors the scenario that we saw with the 2 different coins, where the outcomes, like getting tails, were physically independent. This independence also allows us to factorize the probability calculation. You can check that this gives a probability of about 74% that at least one of them will need to be changed in the upcoming 3 years. However, what if my electrician made a mistake with the wiring? He ended up connecting 2 light bulbs in series on the same circuit. Well, this means that when one light bulb fails, the other receives no current at all. As a result, its lifespan becomes incredibly long. To model this situation mathematically, we could use an exponential random variable with a parameter of 0.01, for example. Well, this implies that once one bulb fails, the expected lifespan of the other bulb is 100 years. That long lifetime is not much of use though, since the bulb never shines anymore. Mathematically, it becomes a bit tricky to describe this with probability density functions. You would need joint distributions, which we will not cover in this video. But you can probably see that computation of probabilities for these dependent random variables will become a lot more complicated, since you can no longer factorize them into probabilities about only one random variable. The main thing for now is that you consider the implications of this setup. The lifetime of these 2 bulbs are now dependent. Indeed, knowing the lifespan of one bulb directly influences the probability related to the other bulb's lifespan. Well, this demonstrates how real-world interactions can lead to dependent random variables. I hope you enjoyed this video. See you later.